For doing number 3 here, we have to build a pattern. We got a good start here. We're taking the sum from 1 to 1. It's just the first term, 1. And then for 1 to 2, you're going to just add the first 2. 1 and 1 gives you the 2. For 1 to 3, you're going to take the first 3 here. I took the total of the first 2 and then added 2. So you're going to see this instead. You're going to see the last total, 2, plus that next, the third one is a 2, to give us 4. Then we're going to take that sum, 4, add the next one, which was 3, giving me 7. 7 plus the 5 is 12. 12 plus the 8 is 20. And then 20 plus the 13 is 33. And those are the sums of this is the sum of the Fibonacci sequence. And notice that n is how many, let me use this here, how many terms you have added together. The first 2, the first 3, and so on. So far, so good? Okay, here's what I want you to do, though. Look at these sums. 1, 2, 4, 7, 12, 20, 33, and compare those to 1, 1, 2, 3, 5, 8, 13, 21, and 34. This is Fibonacci 1, 2, 3, 4, 5, 6, 7, 8, and 9. What do you see? Okay. Does that work for the third one? Yes. So if you took the fifth one minus 1, would you get this total? How about for 4? Would you get the sixth one minus 1? 5 is the seventh one minus 1. Works great. So what the point of this is for you to get this nice little formula, which is going to be the sum formula, is going to be f of n plus 2, what? Minus 1. Good. There's the formula. And that's what you're supposed to do. Hence, express in terms of the Fibonacci number, we did it. Hooray! Are we done? Now, what do we have to do now? Prove it using strong induction. So let's do it. We can handle it. We can handle it, I think. Just to kind of get you started here in proving this, start with your givens. So we have for a given, P of n is that, is what they do. I think it's kind of awkward, but we're given things like if S of 1 equals 1 and S of n equals f of n plus 2 minus 1. Oh, no. No, we're looking at this. And S sub n plus 1 is equal to the previous one, n plus the next term, f of n plus 1. So this is what you do with any sum formula, is you take the sum of all the previous and add the next term. So this is sum previous plus the next term. That's kind of clunky, but I think that's all right. Then what? Then what are we saying? Then S sub n is equal to f of n plus 2 minus 1. That's what you're trying to do. So we start with what we're given, and then this is what we're trying to prove. I'm going to have you come up with your P of 1, proposition 1, and then the assumption. And then we'll get to this one, S sub K plus 1. Oh, let's just do it together. Put that P of 1 in. So when we did P of 1, what happens? When we have n equal to 1, P, the sum is what? The sum of 1 should be what? 1. And if you go sum of 1 is equal to f of the, what would be, third term minus 1. What's the third term in the Fibonacci sequence? 2. So this is equal to 2 minus 1. Is that equal to sum 1? Therefore, true for n equal to 1. I like it. Like it. Works good. And then all you have to do for this next one, I know you don't like this, but S of R is equal to, and F of K plus 2 minus 1. So this is what you think it's going to be, where R is less than or equal to K. And R is equal to 1, 2, 3, all the way to K. That's our assumption part. And now we're going to do my S of K plus 1. And I'm going to start you out here. S sub K plus F of K plus, was it 1? Yeah, next term. Next term, K plus 1. So remember what we did? We added up all those terms, and then I added the next one. So that's what I'm doing here. Substitution? What's a substitution I can make for S of K? Yep, right here. That's my assumption statement. F of K plus 2 minus 1, and then add this F of K plus 1. I'm going to regroup these. F of K plus 1 plus F of K plus 2 minus 1. Joseph sees it? Oh, not yet. Someone's going to see it. What's next? No. Remember, we're talking Fibonacci sequence. What's this equal to in a Fibonacci sequence? F of what? That's right. Isn't it? Isn't the, you add the previous two terms to get the next one? That's what Fibonacci is. 1, 1 is 2, 1, 2 is 3, 2, 3 is 5. Isn't that what's happening here? So is this equal to the sum of K plus 1, which is F of K plus 2 plus 1? Did we prove it? It's the next one. Isn't that amazing? So we would say, therefore, true for, that was, yeah, K plus 1. P of K plus 1. So then we do our big final therefore statement. And we would say, since true for P1 and R equals 1, 2, 3, all the way up to K, R is equal to K plus 1, then P of N is true for all N element of Z plus by math induction.